In the 6.4b lesson, we're going to see how the technique of separate and integrate can be applied in real life situations. For example, radioactivity or half-life isotopes. So we're going to see that. So if you don't have your calculator out already, this would be a good time to grab that because, these questions aren't always going to turn out with the nicest of answers. So you're going to want to be able to use your calculator to evaluate those. One language item to understand is the phrase directly proportional. In math, if anything is directly proportional, that means the relationship is based on a product. It's a constant multiplier relationship. So in this case, we say that y and x are directly proportional to each other based on a constant multiplier k. If you said the variables were inversely proportional to each other, that would look like y equals k divided by x. That would be an inverse relationship. So something would be inversely proportional. But what we're going to be working with specifically is things that are directly proportional to each other. A growth rate can be directly proportional. So if we look at dp dt as a rate, that's here, it can be directly proportional to p, which means that there's that k value that's related. And we've seen previously that we can work to separate and integrate that. And the result is the exponential growth relationship, p equals a constant times e to the kt. So directly proportionality from the rate to the population can lead to exponential growth. Actually, I should clarify. We use exponential growth as a word only if k is positive, but we say exponential decay if the k value that we are finding is negative. So k being that multiplier at the beginning, if that k value is positive, that will lead to growth. If the k value is negative, that will lead to decay. So let's look at how we get from the proportional relationship to an exponential relationship. So if we look at the proportional relationship given here, dp dt equals kp, that's a direct proportional relationship. If we separate, so dp over p and k dt, we can separate that. This is going to lead to an exponential relationship, okay, the proportional relationship leading to exponential. So we're going to integrate both sides. That'll give me the natural log of the absolute value of p, and that will give me kt, plus a constant c. Now, we can find our c with our initial condition. We've been given the initial population p sub 0 when t equals 0. So we can say the natural log of p sub 0 is going to equal k times 0 plus c. Well, that clearly shows us that c is equal to the natural log of p sub 0 value. So that's the starting population value, the natural log of the starting population value. So we can go back to ln of p equals kt plus, now we have the ln of the absolute value of p sub 0. And now if we want to get p by itself, we exponentiate on both sides with parentheses. Okay, so there's one e on each side, parentheses on each side. That gives me the absolute value of p equals e to the kt times e to the ln of p sub 0. Remember that addition within the exponent is the same as multiplication. Then I can use the fact that e and ln are inverses of each other. So I have this e-ln combination here, which invert each other, and you're left with the absolute value of p equals e to the kt times p sub 0, absolute value. And we are, I guess, working under the assumption that population is always a positive number. We don't really ever have any population that goes below 0. So we can assume that the absolute values are going to not be needed. So p equals, and I'll put the p sub 0 in the front. So that gave us the exponential growth model, that any population can be found if we know the initial population and we know the value. So let's take an example from a chemistry lab. We are given an exponential growth model, and the growth rate has a constant of proportionality. So this negative 3.5, we know that that is what's called K. So K is negative 3/5. We also know that the chemical compound that's present starts with 100 grams. So P sub 0 equals 100 grams. So we can write an exponential growth model. So the amount of the chemical compound is equal to the initial amount of the chemical compound times e to the negative 3/5 of t. And that's the model. Now, if you forget, if you can't happen to remember that particular formula, you can start with dp dt as the rate being equal to negative 3/5 of p. So that's the proportionality constant that's multiplied. And you can do a separate and integrate. So dp over p equals negative 3/5 of dt. And you can integrate both of those. And you will end up with the exact same value, or the exact same expression that you started with. So the amount of chemical compound present. So it's up to you how you want to do that. If you want to memorize where K and P go, that's fine. If you want to develop the using the separate and integrate technique, that's fine as well. So the same thing is applicable in radioactivity. Radioactivity usually is typically decay. When things are radioactive, that's typically a decay situation. In rare situations, the radioactivity grows, and so we have exponential growth, but typically the radioactivity dissipates and gets less over time, and so that would be a decay situation. Interesting with those chemical compounds, as they decay, they turn into something else. Radioactive carbon-14 turns into nitrogen as it goes through the decay process. Radium, as it goes through the decay process, turns into lead. So yeah, just interesting chemistry, how those molecules realign and end up in a different structure. But a lot of times when you're talking about radioactivity, you're talking about a half-life. And a half-life is the amount of time it takes for the value to be cut in half. That is called the half-life. So if it takes you, if you're measuring, 20 grams down to 10 grams, then how much time does that take? To cut the value of the amount in half, the length of time is called the half-life. Every isotope has a different half-life. There's no universal half-life. It's all dependent on the different elements that you start with. We can find that with calculus. So if we know that something is decaying according to a differential equation, we can find the half-life of this particular one happens to be samarium. Okay, and so we could say let's figure out how this is going to work to find the half-life. Well, we have our model, and our model has this value here, which is taking the value of K. So we know that K is equal to negative 0.0077. So we can write a Y model. So Y would be equal to Y sub 0 e to the negative 0.0077 t. We don't know how much we're starting with. Y sub 0 is a mystery. So as of yet, our Y sub 0 value is unknown. But that's not going to stop us. With any unknown value, decay, we want to get down to half of that unknown value. So if the unknown value is 100, we want to get down to 50. If the unknown value is 8, we'd want to get down to 4. Regardless of the exact value of the initial amount, we want to get down to half as much. And so we can say if I start with Y sub 0 in the equation e to the negative 0.0077t, how long will it take me to get down to half of Y sub 0? In other words, Y sub 0 divided by 2. That would be half as much. Again, we don't know the specific amount, but we can do it in an arbitrary value. And then we want to solve for t. That's the question. Find the time that it would take to have for that to happen. So we can divide by Y sub 0. And we end up with half equals e to the negative 0.0077t. And that's a quick ln. I've got the natural log of half would be equal to negative 0.0077t. So solving for t is going to be the natural log of half divided by negative 0.0077. So this is where your calculator would come in handy so that you could evaluate what the actual actual half-life would be. So I'm going to check what ln of 0.5 divided by negative 0.0077. So it turns out to be 90.019 years. So this particular isotope takes over 90 years to decay to half of its present value. Now look at what that ended up as. Natural log of half over the constant. That can be generalized. The half-life can be found as the natural log of 2 divided by k, as long as k is positive. Interesting, because our k last time was negative, but we divided by the natural log of half. Do you remember what the natural log of half is? The natural log of half is the natural log of 1 minus the natural log of 2. The natural log of 1 is 0, so I have negative natural log of 2. Negative natural log of 2 over the negative 0.0077. So this also turned out to be the ln of 2 over the k value. Worked out the same.